Well, hello everyone. Now, in the past, I've done a lot of talking to you guys about IGBTs and how to use them and some of the problems with them and some ways that you can get around those problems, and we've talked about cooling and gate driving and inductance and all sorts of different aspects about them. But today, I wanted to speak to you a little bit on something that I haven't before, and that is some of the noise that comes along with switching an IGBT. And by noise I mean the interference that the IGBT makes because of its switching. Now the IGBT, when it switches, can interfere not only with other devices, but it can also interfere with itself, and it can interfere with the circuit that's controlling it. So first I want to start by giving you a simple little demonstration. So what you can see is we got the oscilloscope, we've got rectifier, IGBT, simple capacitor, and a resistor there, and AM radio. And what I'm going to do, I'm going to turn that on. I'm going to show you what it does to an AM radio signal, and then we'll get a close-up on the oscilloscope. So that's AM radio right now, but what happens when I start using the IGBT? So as you can tell, it just completely destroys the AM radio signal. Now I'm going to turn on the IGBT again, and I'm going to let you look at the oscilloscope. Okay, so the IGBT is running. It's switching power into the heater, and you can see the pulse width modulation signal on the oscilloscope, but let's take a closer look. So as you can see, it's not really switching with very much difficulty. There's not much turn on voltage, there's not very much turn off voltage either. So it's not like we're switching a huge amount of power here. But the thing is though, when there is a turn off voltage spike, when you use an inductive load, then the noise starts to get louder and louder, and the IGBT may interfere with itself. If you're using a dual IGBT, and the lower element can interfere and switch on the upper element, or the IGBT can even turn on or turn off its own controlling computer or pulse width modulation generator or synthesizer or whatever. It may interfere with that, and it may cause its own destruction. So today I want to show you a method to separate the synthesizer, PWM synthesizer or microcontroller, from the IGBT without picking up more noise. Okay, so there's the input rectifier. It's the half-bridge IGBT, which switches the power into that heater, and the gate driver. So we know we can't just set the PWM generator or microcontroller right next to it, because it took out the AM radio, and it's not likely to play very nicely with a microcontroller. But we can't just use wires made of copper, because those will just pick up more interference. Those would just be like big long antennas. So instead we'll have to use this. These are fiber optic cables. And in just a second here, I'm going to show you how they work. Okay, so you see that end of that fiber optic cable there? It's pointing at that box. What I'm going to do, I'm going to stick the other end up to a laser. You see the light come out of it. And it's just that simple. Now if you get your hands on a nice piece of industrial equipment like a big ABB motor controller, and you look inside of it, you'll find a bunch of these little fiber optic cables. The switching noise from the IGBTs inside is so severe they had to separate it. and they use fiber optic cables to communicate with the IGBT's gate driver, just like we are right here. And this is all it is. It's not complicated at all. So I have a little microcontroller. The output goes to a fiber optic LED. And that signal, that PWM signal, is just sent all the way over there to that phototransistor on that gate driver board. So now the distance isn't nearly as limited, and it's optically isolated, so there's no electrical danger here. So even if we hook it up to a gate driver of an IGBT that's, say, 6,000 volts, and we start switching it, even if something goes wrong, this isn't going to shock us. So we can manipulate the microcontroller, and we can reprogram the microcontroller, and it's not going to hurt us, and we're not going to pick up any additional noise. So that microcontroller way back here is not going to be picking up that noise, and we could put that inside of a metal box. We can move that even up to a kilometer away, and it's still not going to be affected by the switching of the IGBT, because this fiber optic cable doesn't transmit electricity. So let's have a look at what the controller actually does. Okay guys, bear with me. I'm going to try to show you the output of this fiber optic LED. See? As you turn the pulse width up, it just gets brighter. And that's all it is. It's just an LED. It's like an LED on a dimmer is all it really is. That controls that IGBT. And it's just sent down that fiber optic cable. And these are your cables. So the gray is transmit and the blue is receive, and this one has two of them in it. So if the IGBT gate driver outputs a fault signal, it can send a pulse back to the microcontroller. So I hope you guys enjoyed it, and I hope you learned something today. You can feel free to ask me any sort of questions, and I'll see if I can answer them as best as possible. And I thank you guys for watching.